Welcome to Calc 3. This is section 13.7, Cylindrical and Spherical Coordinates. There's one video in this on this section. We'll combine both the theory and the examples in this video. So to start out with some definitions, cylindrical coordinates and spherical coordinates. So cylindrical coordinates are on the left here. We think of cylindrical as like a soda can with a base that looks like a circle. So x and y look like our circle coordinates. X equals r cosine theta, y equals r sine theta. And our z-coordinate is just the height, z. So no great change there. R is equal to r squared, rather, is equal to x squared plus y squared. R is positive, and theta goes from 0 to 2 pi. Our Jacobian is similar to our polar coordinates, r dr d theta, and we just tack in the dz as well. For spherical coordinates, we are looking for a sphere, so we have the radius, which shoots outwards, theta, which shoots around the sphere, and phi, or phi, sometimes pronounced, which starts at the top of the sphere and swings down from the top of the sphere down to the bottom of the sphere. So for our spherical coordinates, we have x is equal to rho sine of phi cosine theta, indicated here. Sine, or y is equal to rho sine of phi sine theta, and z is rho cosine of phi, and our Jacobian is rho squared sine of phi d rho d phi d theta, where we have rho squared is equal to x squared plus y squared plus z squared. Rho is positive, or 0. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. One thing to note is that the notation may be different in your electromagnetics class if you're going on to this course. It may be different in different engineering fields, so please keep that in mind. So let's go ahead and start working examples. So let's find the mass of a solid bounded by two cylinders. So let's suppose that we have cylinders x squared plus y squared equals 4, and x squared plus y squared equals 1 between the planes z equals 0 and z equals 10 with a particular density. So if we set this up, we can look at our kind of diagram here. So on the xy plane, we have our cylinder with radius 1, and we have our cylinder with radius 2. And so we're looking at our projection, where if we think about z as projecting out of this board, we're looking at the area between these two cylinders. And so if we think about this as two circles, our radius goes between 0 and, goes between 1 and 2 at the edge of our circles. So radius goes between 1 and 2. Our theta goes around the circles, so between 0 to 2 pi, and our z goes from the height of 0 to 10. So using cylindrical coordinates makes it so we don't have to worry about any square roots for our x and y functions. So then we set up our integral here. We set up 0 to 10, or we can set it up in any particular order, so long as we're careful with our notation, but let's follow our Jacobian. 0 to 2 pi, 1 to 2, and then we have 0 to 10, and then z times our Jacobian, r dz, dr d theta. And so so we get 10 squared over 2. So let's see, 0 to 2 pi, 1 to 2. So z squared over 2, so that gives us 100 over 2, which is 50 r dr d theta. So now we get r squared over 2. So 0 to 2 pi, so r squared over 2, so that's 25 times 4 minus 25 times 1 d theta. So this gives us 75 times 2 pi, which gives us 75 times 2 is 150 pi as the area between these two of this particular solid with this density function. So let's look at another example here. Let's find the volume of the region bounded by these particular surfaces. So we have z squared equals x squared plus y squared, z equals 1 and z equals 0. So this looks like a cone. So this is z equals square root of x squared plus y squared. This is z equals 1, and this is the line z equals 0. So if we are looking at this particular function, we know that r squared in cylindrical coordinates equals x squared plus y squared. So we can bound z, if we think about our rectangles going from the line z equals square root of x to squared plus y squared, think about our rectangles looking this way, we can say that z actually goes from r squared, this piece here becomes r squared, z is equal to r, goes from r to 1. And since z starts at 0, that means that r goes from 0 to 1. And since we're looking all the way around, we have that theta has to go from 0 to 2 pi. So setting up this integral, we have 0 to 2 pi, 0 to 1, r to 1 of r, dz, dr, d theta. We have no density function, so we assume the density is 1. So 0 to 2 pi, 0 to 1 of r minus r, r minus r squared, dr, d theta. So this gives us 0 to 2 pi of 1/2 minus 1/3 d theta, which gives us 1/6 times 2 pi, which gives us pi over 3 as the area of this chunk of the shape. And so it's important to note here that what we did is we turned our shape as kind of this slice of a sphere as a into cylindrical coordinates, and that made our life a lot easier. So let's look at another example. Let's find the mass of the region bounded below by this cone, the similar shape as we had before, and above by the top of the sphere, x squared plus y squared plus z squared equals 1. So this is a sphere with radius 1 with a density function delta of xyz equals z. So when we start dealing with spheres, this looks like perhaps an option to use spherical coordinates. So x squared plus y squared plus z squared is equal to rho squared. So rho equals 1. So we know that rho is an upper bound here. So if we substitute in our, let's recall our spherical coordinates. So x is equal to rho sine of phi cosine of theta. Y is equal to rho sine of phi sine of theta. Then z is equal to rho cosine of phi. And so when we're looking at this particular piece, we know that we have x squared plus y squared equals plus z squared equals 1 is rho squared equals 1. And then if we take z squared is equal to x squared plus y squared as our other bound from our other bound, so our lower bound, we can substitute in our definitions of our spherical coordinates. So z squared is equal to rho cosine of phi squared, and then x squared is rho sine of phi cosine theta squared plus rho sine phi sine theta squared. So substituting in these pieces, so each piece will have a rho squared, so we can divide through by the rho squared, but let's go ahead and see that precisely. So rho sine of phi rho squared cosine of squared of phi, rho squared sine squared of phi cosine squared theta plus rho squared sine squared of phi sine squared of theta. So we can cancel out all the rho squareds. And then we also see that cosine squared plus sine squared, we can factor out the sine squareds, and we're left with cosine squared of phi is equal to sine squared of phi times cosine squared of theta plus sine squared of theta. But by our Pythagorean identity, this piece is equal to 1. So this gives us that sine squared of phi equals cosine squared of phi, which means that tangent, if we divide both sides by cosine, tangent squared of phi equals 1. So if tangent squared of phi equals 1, this means that phi equals pi over 4 is a bound. Because to solve this, tangent squared of phi equals 1 means that tangent of phi equals 1, and tangent of phi equals 1 on the domain 0 to pi over 4, pi, or 0 to pi for our domain for phi means that pi over 4 is a bound. So this is helpful. So since we're looking at the entire circle in the xy plane, we've got an idea of our bounds here. So what we've done is we've used our bounds on the problem to develop our bounds on the interval. So we know our rho goes from 0 to 1. We know our theta goes from 0 to 2 pi since we're going around the entire sphere. And our phi goes from 0, our lower bound, we're starting at the top of the sphere, and we're angling down to pi over 4. And we can think of this actually looks like an ice cream cone. So we have the cone on the bottom and the ball of ice cream on the top. So as we're integrating this, we have 0 to 2 pi, 0 to pi over 4, 0 to 1 of rho cosine of phi. This was our density function z. Right? We want to make sure we keep it all in the correct coordinate system. Times our Jacobian rho squared sine of phi du rho d phi d theta. So theta there doesn't show up anywhere else in this problem, so we can pull out the 2 theta or the 2 pi. It's separable, so we can pull the theta all the way out front. This comes from our theta bounds. So this is as if we were to evaluate the outermost integral because there's no thetas. This is all a constant in the inside with respect to theta. So we can solve all of this inside piece, and then we know the theta bounds is 2 pi. So versus we can't do it with rho because rho shows up in the problem and phi shows up in the problem. So those pieces may relate to each other. But theta does not show up anywhere in the problem, so everything else is a constant with respect to theta. So we can multiply that 2 pi and simplify our problem to start. So combining some terms, we get rho sine cosine, or excuse me, rho cubed cosine of phi, sine of phi, du rho du phi. So rho cubed goes to rho to the 4th over 4, so we get 2/4 rho to the 4th times pi, and so this gives us 2/4 pi times 0 to pi over 4 cosine of phi sine of phi d phi. And this is a perfect place for a u substitution. So this gives us 1/2 pi. And if we let our u piece be sine of phi, then our du is equal to cosine of phi d phi. So then our integral of u du is equal to 1/2 u squared. So this gives us 1/2 sine squared of phi evaluated from 0 to pi over 4. So then we get pi over 4 sine squared of pi over 4 minus sine squared of 0 is 0. So sine of pi over 4 is square root of 2 over 2. So we get square root of 2 over 2, so that's 2 over 4. So we get pi over 8 as the area of this ice cream cone. So if you have any questions, as always, feel free to ask.